Okay, now let us consider in temperature Ts instead of that standard value 290 Kelvin, and in that case let us see what happen SNR, how to calculate. So, SNR at the output, this is equal to Ps divided by K into Ts plus F minus 1 T naught into Bn. So, the first term, this is due to the source temperature Ts, and the second term, this is due to the effective noise temperature Te. So, if I now assume that Ts equal to T naught, in that case Ps by K into T naught Fbn. So, sometimes we simply write down that SNR at the output, this is equal to Ps by K T naught Fbn, but that happens only if Ts is equal to T naught, and if the source temperature is different than that 290 Kelvin or T naught. So, we have to use this correction factor, and this overall expression we have to consider the effect of Ts as well as Te separately. So, considering a scenario like that, we can calculate the we can define a parameter which we call the operating noise factor NOP. So, how we do it? Operating noise factor of a combined system including the source and the receiver is the ratio of the actual available output noise power density, which is given by NOA, to the available output noise power density if the receiver had no internal noise source. So, that means in this case what we will be doing? We are considering actual temperature, not T naught, so Ts, and then calculating what is the available noise power density at the output. And in the second case, again we are recalculating it, but we are assuming the receiver itself is noiseless. Then what is the effect of that left hand side noise and how it is being transferred to right hand side? Then we take the ratio. So, it is given by FOP, this is equal to NOA, which is the available output noise power density. So, it includes both the contribution from left hand side and due to the receiver itself, and divided by GAKTS. So, GAKTS, you see here we did not consider any internal contribution of noise. So, this is only due to the left hand side. So, FOP, it takes into account the actual source temperature Ts. So, why we are doing it? Because let us say you have designed the receiver, you have the noise figures or let us say noise factor whatever specified by manufacturer, that is for a standard value 290 K, and now for your system, which may be it may operate let us say for space application, it can operate at -50 -60 Kelvin, -50 -60 degree centigrade. So, or it can be at very high temperature scenario. So, for that case you recalculate what is the SNR for your receiver chain. So, then SNR at the output, this is equal to the GAPS, this is the output power divided by output noise power. We are expressing it in terms of FOP. So, then this is equal to simply FOP GAKTS into Bn over a noise bandwidth Bn, or GA cancel out. So, PS by FOP KTS Bn. Now, PS divided by KTS Bn. So, this KTS Bn, this is actually the noise present at my left hand side of the receiver over a bandwidth Bn. So, simply then PS divided by KTS Bn, this factor we can call SNR at the input side. So, we can simply write down F operating, that is equal to SNR at the input divided by SNR at the output. not at the standard temperature, but at any given temperature. So, that is how we can define another parameter F operating noise operating noise factor. So, now in presence of receiver noise N internal, in the previous one when we calculated K, we put simply K TSBN. Here we did not consider effect of internal noise generated inside the receiver. Now we are introducing that. In that case, F operating, this is equal to N internal plus, so this you see noise factor, this is SNRI by SNRO. So, in terms of noise, simply then we can write down noise at the output divided by noise at the input. So, noise at the output, this is GAKTS plus the internal noise divided by noise at the input GAKTS. So, this is 1 plus TE by TS, where we are putting N internal equal to GAKTE. Now, already we have seen that TE in previous expression, TE equal to F minus 1 into T naught. So, we can also express F operating, that is equal to 1 plus, we are simply just putting the value of TE in the previous expression. So, F minus 1 into T naught by Ts. In this expression, it simplifies to F, or F operating, it becomes simply F only when Ts is equal to T naught. Also we have seen it previously. You see, it simplifies to this SNR at the output. In this expression, it simplifies to K T naught FBN only when Ts is equal to T naught. For this case also, F operating is equal to F that specified only when Ts equal to T naught, otherwise not. So, now let us say Ts is not equal to T naught. So, then we have to consider all the effects of Ts, Te, and T naught is already given or specified for the components whatever we are using. So, so many noise temperatures we have to deal with. We can simply eliminate Te by introducing one more new parameter. So, define a system noise factor N system to eliminate Te for simplification. So, F system, how we are defining F system, that is equal to Ts plus Te by T naught. So, putting the value of Te here, F system, this is F minus 1 plus Ts by T naught, or we can write down then SNR at the output, that is equal to Ps divided by F system K T naught Pn. You compare this expression with the previous one for a noiseless receiver. So, for noiseless receiver, SNR at the output is equal to Ps by this factor, but here this is Ps by F system, not F operating, if we have a noisy receiver, which is the practical scenario. So, F system where it is related to FOP by FOP into Ts by T naught. So, if we know F value given for T naught, then we can easily calculate F system from this expression FOP into Ts by T naught. Now, noise figure for a cascaded system. We already calculated equivalent noise temperature for a cascaded system. Now, we are going to calculate noise figure or noise factor for a cascaded system. So, basically overall SNR calculations, we can use any of these two approaches, noise figure approach or noise temperature approach. Noise temperature approach already we know. Now, we are going to see the noise figure one. So, we are considering a simple scenario. We have, let us say, just two amplifiers in cascade it can be any other components also. Simply we have to calculate its gain. The first one, let's say gain is GA1 and it's providing some internal temperature N internal 1. So if I express in terms of noise temperature, you remember we expressed it by TE1, then N internal 1, that is equal to K TE1. The second component, it is GA2 gain and internal noise generated N internal 2. So N1 whatever falling on left hand side to the second component. So this is the output noise power from the first component. So if I now first consider a noiseless component, that means N internal 1 or N internal 2 is 0. In that case N1, this is equal to then Ni multiplied by gain of this amplifier. So that is the noise available at the output. We consider a noiseless system. So that output is falling on the second amplifier. So N1 equal to GA1 Ni. Similarly N2 equal to GA2 N1, that is equal to GA2 GA1 Ni. Now let us consider the effect of N internal 1 and N internal 2. So considering noise introduced by the elements N2, that is equal to N internal 2 plus GA2 multiplied by whatever noise coming from left hand side, N internal 1 plus GA1 Ni, or we can write down this is equal to then N internal 2 plus GA2 into N internal 1 plus GA1 KT naught. So Ni we are representing by KT naught. Then the standard cascaded noise factor, this is also the Friis formula, the second form for noise factor, F equal to N2, so output noise power divided by GA2 GA1 KT naught. So we can now put the values here. N2 already we calculated in the previous one, N internal 2 plus GA2 N internal 1 GA2 GA1 KT naught divided by GA2 GA1 KT naught. So if I consider the first two terms, N internal 1 and GA1 KT naught, so GA2 this is cancel out, and sorry, this is for the, we are considering this, sorry, second and third term. Now if I consider the first term N internal 2, with that we are simply adding and subtracting GA2 T naught. So original term is N internal 2, then plus minus GA2 KT naught divided by this. So it simplifies to F1 N internal 1 plus GA1 KT naught by GA1 KT naught, this is F1 plus F2 minus 1 by GA1. So this is for a two component system. If we have n number of components, you can simply add other terms. So then the third term it will be F3 minus 1 divided by GA1 GA2. Similarly you can define it for nth number of term. So again what we see that the contribution of first component, it becomes very important. So for all other components it is being divided by the gain of the other components, preceding components. So that's why whenever we use an amplifier, it should be a low noise amplifier just immediately after the antenna to decrease the overall noise figure of the receiver. So, now we learned how to calculate the overall noise figure of a receiver, noise factor of a receiver, and if we simply convert it to decibel scale, then we will call overall noise figure of the receiver. So, it will determine the noise floor below which the receiver it can't detect any noise power, any signal power. So, minimum SNR that should be higher than this. Also we have we learned what is link margin. So, this value is not sufficient for any wireless system. So, above that we have to maintain a link margin of 3 dB to 10 dB for. Now, let us take one example numerical with numerical values. Let us say one antenna, it is directly pointing towards earth. It can be a radiometer itself, this whole receiver chain together with antenna. So, in radiometer applications, it is actually one type of passive imaging. What is done? Simply the power whatever radiated by earth's surface, it is collected by antenna, and then it is converted to some effective noise temperature. And now, if we point towards different direction, so depending on the dielectric constituents of the earth's surface and the roughness of earth's surface, the effective noise temperature will change, since the input power will change. So, that is how we can map any given earth surface, and it is a very popular in remote sensing application. We can monitor sea level, we can monitor ice level, and many other things. So, this is one such application. So, antenna is directly pointing towards earth, and the earth temperature, physical temperature is given as 300 Kelvin. So, it is not also a perfect black body, because it's given by characterized by some emissivity epsilon. So, emissivity for black body equal to 1. Now, emissivity it can be given by 1 minus rho, where rho is the reflectivity. So, if epsilon is 0.9, that means rho is equal to 1 minus 0.9, which is 0.1. So, a good emitter is a bad reflector. So, this antenna is connected to a circulator by using a section of transmission line, maybe a cable or waveguide section. Starting from antenna to circulator, they are at a physical temperature given by 180 Kelvin. It is quite low, but it may happen in space. The loss of this connecting section is given as 1 dB. We also have some loss from the circulator, which is given by 1 dB. And look at the antenna. Antenna efficiency is 95%, or rho e, it is given as 0.95. Immediately after the circulator, we have a low noise amplifier. So, this gain of this low noise amplifier is given as 20 dB, and the corresponding noise figure, not factor, in dB. Noise figure is 4 dB. Again, we have some loss due to connecting sections, that is 1 dB, and next we have one mixer. It is down converting the millimeter wave signal coming from left hand side. So, for the parts, this LNA and the connecting cables, they are at a physical temperature at 250 Kelvin, but right hand side maybe they are sealed inside one package. For them, they are at a thermal equilibrium of physical temperature 400 Kelvin, it is quite high. So just after mixer again we have a connecting section, then the IF amplifier, which is obviously a low frequency amplifier. So for this low frequency amplifier, noise figure is given as 3 dB, gain 60 dB. Now when we convert this noise figure to noise factor, obviously log base is 10, we have to take 10 to the power, but we are dealing with power, not voltages. So that means we have to divide all these values by 10, not 20. For example, if I want to convert this 4 dB noise figure to corresponding noise factor, what we have to do? 4 by 10.4, so it will be 10 to the power 0.4. Now what we have to do? We have to calculate what is the overall SNR. That also we can calculate if we can calculate what is the overall effective noise temperature TE of this system. So we will start from the from the source. Basically, before antenna we have source, the earth surface. So the earth surface temperature is given 300 Kelvin. Now what happened? You see, if I look at the power whatever received by antenna, some part is due to emission due to the earth itself, and another part which is coming from the dwelling radiation from atmosphere, that is being reflected by the earth surface and coming to antenna. But since its rho is 0.1, it is a poor reflector, and looking at the roughness of earth surface, we are simply neglecting that reflected power part. It's in practice also it is negligibly small. We will be considering then only the effect due to this emission from earth surface itself, which we are considering as a gray body. So this effective radiation will be represented we will be representing by a resistor. So this is the figure. So for this part, what we are doing, we are considering the first part starting from earth surface to circulator, which are at a physical temperature of 180 Kelvin. Now how to calculate T external? T external is simply epsilon into T physical. So temperature of earth surface, it is given as 300 Kelvin, put epsilon 0.9, T external, it becomes 270 Kelvin. We are using temperature approach. Now antenna temperature, T antenna. So antenna loss is given by 1 by rho e, because gain is 0.95, then loss it is 1 by 0.95, then followed by antenna we have a section of waveguide for which again loss is 1 dB. So we calculate then what is the corresponding gain. So it is 1 by 10, that is 0.1, so 10 to the power 0.1. So overall gain G1 into G2 for this two cascaded system. So G1 into G2, so G1 you see 0.95, G2 0.794, G1 2 then it becomes 0.754. Now loss L12, it is simply 1 by overall gain, it is 1.33. So we calculate then T antenna, it is equal to, we already have seen the formula, T E equal to T physical into L minus 1. So put it there, T antenna it becomes 59 Kelvin. Then the source temperature Ts for these three components all together, this is equal to G12 multiplied by T external, because you see the noise generated by this external source or the resistor, it's being propagated through antenna and that waveguiding section. So Ts equal to G12 into T external plus T antenna, or put the values, it becomes 248 Kelvin. So Ts is 248 Kelvin. Here we did not consider any direct contribution of sunlight. Actually, sky is very cold. If you point your antenna towards earth, will receive more power compared to if you just point your antenna to cold sky. So cold sky temperature is typically very low. Equivalent noise temperature is 50 Kelvin. So the source part calculation is over. Next part, we have to calculate TE and hence T operating. So we have to consider the contribution due to LNA, then the connecting section, mixer, connecting section, and then the IF amplifier. Oh, before that we have circulator also. So among these, mixer specification, it's given its temperature ratio. You see here, L equal to 5 dB. That means conversion loss is 5 dB and temperature ratio is 1.5. So actual its operating temperature is 290 multiplied by 1.5. Okay, let us take 5 minutes break, then we will continue the calculation.